Hey everyone, welcome to a supplemental practice video on how you can use our flowchart to determine the relationships between compounds. So what I've got here to start is a typical question that you might, and let's be honest, will almost certainly see from me coming up on the exam. I might ask you to determine the relationship between the following two compounds. So if you see something that's worded like that, then you have to think, okay, this is the time where I need to go through my flowchart and decide what the relationship is between two compounds based on what their formula is, how things are connected, and what the arrangement in space might be. So here's a little refresher on our flowchart. You can find this either in our lecture notes, maybe you rewrote it for your own notes, or I can post this as a separate PDF just so that you have this as well. Again, you won't be able to use this on your exam, but as we go through these practice examples and you answer the questions that kind of come from this flowchart, you won't need the flowchart. You can just go through the process instead. So we're going to go through, like I said, this flowchart step by step to find the answer to these practice questions. So example number one. We have two molecules here that seem to be mostly carbon chain and some chlorine atoms on them. So I've tabulated up the questions down here that come from our flowchart. So let's return to the flowchart just briefly to remember what it is that we're looking for here. First, we have to decide if they have the exact same atoms or not. This is by looking at their formula or kind of tabulating up a formula if you prefer. If they don't have the same formula, then they're totally different, right? And so they're different molecules or different compounds. But if they do have the same formula, then there's some kind of isomer. And so we need to figure out all the different types of isomers and decide which category our molecule of interest fits into. So we need to check to be sure that they're connected in the same order, because if they're not, then they're still pretty different. They're what we call constitutional isomers over here. But if they are connected in the same way and they have all the same atoms, they're stereoisomers. And then we just have to figure out which type of arrangement in space we're dealing with. If there is a double bond or ring present, then we might have cis and trans isomers, but these are just types of stereoisomers. And if not, then we probably have a chiral center, and we need to decide about R and S to determine whether or not we have on our hands a pair of enantiomers. So back to the original question. So let's look and see if these have the same chemical formula. Now you can, as I said earlier, just count up all the atoms if you like. You can simply look for the same major pieces, whatever makes the most sense to you. Let's really count everything out for this first example, and then maybe we'll start skipping over that in the next coming examples. So let's count up all of our carbons, hydrogens, and it looks like there's one chlorine on both molecules, so that's a good start. So I'm going to just label these with some C's here. 1, 2, 3, 4, 5. So it looks like 5 carbons here. C5. This one has 1, 2, 3, 4, 5. All right, good so far. And normally, if you don't see any other differing patterns of multiple bonds or rings, they're likely to have the same number of hydrogens, but let's just count it out really quickly to be absolutely super duper sure. When I draw in my hydrogens to count them, I don't bother drawing in the whole hydrogen. I just draw in a little tick mark like this to remind myself there's, hey, 1, 2, 3 hydrogens at that position, and then I make sure to go back and erase them later so that they're not misconstrued as an extra carbon. But that's what I do, just little tick marks to remind myself. There's 1, 2, 3 there, there's a dashed hydrogen there, and then 2 here, 2 here, and 3 here at the end. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11 by my count. And like I've said before, I'm not always the best at counting, so make sure you're double checking my answers here. All right, let's see if that's the same on our second molecule. 1, 2, 3, wedge hydrogen here. 4, 5, 6, 7, 8, 9, 10, 11. Looks good. And last but not least, well, actually most importantly, when it comes to our priority rules, we have a chlorine on each of these molecules, so they do have exactly the same formula. And again, feel free to do this tabulation. You may also be able to just recognize that by looking at the molecules that they're similar enough that they have exactly the same number of hydrogens, carbons, and that chlorine atom to them. So whichever method works the best for you. Now we need to check and see if they have the same connectivity. So what does that mean? I like to use the word connectivity, but I think it's a little bit of a weird word. So let's just re-explain from our previous video that when I say connectivity, I mean, are all of the carbons, hydrogens, and chlorines connected in the same way? So one way you can do this is by just evaluating the shape of the molecule and see if that's similar. Here it looks like a linear molecule in both cases, so that seems pretty similar. But then we have to check and say, okay, where is the chlorine, where is that interesting functional group connected? And maybe use some numbering here to help you decide. So what I would like to do is put our numbers on here just to say there's 5 carbons. We're not going to name this or anything, but there's a 5 carbon chain, and at carbon 2, we have a bond to chlorine. Now, is that the same over here? Well, it doesn't look like it if I number it this way, right? Because it looks like our chlorine is on carbon number 4, and that would be different. But if I number it from the other direction, then it does end up being exactly the same. The carbon 1 is a CH3 group. Carbon 2 has the bond to chlorine. Carbons 3 and 4 are CH2 groups. And carbon 5 is a CH3. So when you tabulate it up like that, they have exactly the same connectivity. Now, connectivity doesn't take into account the wedge and dash. So you don't have to worry about that yet. That's going to be more down here in step number 4. So we'll get to that in a moment, but we have to check to see if we have any rings or double bonds first. Because if we have one of those, then we're most likely looking at cis-trans stereoisomers, but I don't see any rings here. I don't see any double bonds, so we don't have to worry about that. We'll move on instead to see if we have a stereocenter and see if we have both R and S isomers present. So let's try to find a stereocenter, shall we? As I've said in the previous videos, they're almost always going to be at these places where I've already labeled a wedge or a dash for you. So carbon number 2 looks like it's probably going to be a chiral carbon, but you want to just check to make sure that it has 4 unique substituents all around that carbon to be sure that it isn't a dud or a little trick that Grace put in there for you. So let's look and see what different groups we have around these carbons. So first things first, we have the most interesting chlorine group there. We have a hydrogen, that's definitely different. And then the carbon groups, you just want to check to make sure the carbon groups are different, or maybe they're not. Here we have, like I said, the CH3 group, so that's a methyl group. And then on this side, we have a 3 carbon chain or a propyl chain. So they're all different. We have chlorine, hydrogen, methyl group, and a propyl group. So that's 4 different things. So these are, in fact, true chiral centers, and those stars can stay. And of course, the same is true for this molecule over here because it has all the same groups and the same connectivity. We've already confirmed that by looking at numbers 1 through 3. So now, all we need to do is see if we can assign R and S. If we have both R and S, we'll have a pair of enantiomers. If we have the same letter twice, we'll have the same compound. So let's assign our priorities and decide on R and S. So chlorine is the highest atomic number of all of the elements present here. So chlorine is going to be number 1, and poryl hydrogen is always going to be number 4. Then we have to decide between methyl and propyl. And between those two, whichever has the most bonds to higher atomic number things is going to be higher priority. And that means more bonds to more carbons. So that means our propyl group will be higher priority, priority number 2, where the methyl group will be priority number 3. So we can go ahead and start thinking about our circle that we're about to draw, but we first have to check to make sure priority number 4 thing is going away from us. It's a dash in the back. It's good. So we can go ahead and assign our circle as we see it by drawing from 1 through 2 to 3. And so that is going clockwise, right, or the right way around a clock. So this is an R chiral center. Now let's see if that's the case for this other molecule. We have already assigned the priorities, so this one should be quick. We have chlorine at 1, hydrogen at 4, our propyl group over here is 2, and the methyl group is 3. But now we have to check ourselves. The hydrogen is sticking out of the page at us, so whatever circle we draw, we're going to have to switch our answer because we're looking at this sort of from the backwards side. So if we go from 1 through 2 to 3, that still looks like R, but it is actually S because we have to flip our answer for that wedged hydrogen. So this is S. So if we have both the R and the S isomers present, then we know our final answer is that we have a pair of enantiomers on our hands. And for these questions on the exam, they will probably be in the form of multiple choice or short fill in the blanks. And I will ask you to use the letter E for enantiomers. How did this one go? Did this make sense? Let's try another one together. If you would like to pause the video here and make a guess about which type of stereoisomer that you think this is, go ahead and do that now. Then we'll work through the same flowchart questions all together. All right, let's see if we have the same formula. This one sort of feels a little bit trickier to me just because the shapes look a little bit more different. So let's count up the carbons and we can check our hydrogen count as well. So here's 1, 2, 3, 4, 5, 6, 7, 8 carbons, and 1, 2, 3, 5, 6, 7, 8, 9. Is that right? 1, 2. See, you have to double check your counts sometimes. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I thought this one had 9 carbons in it. That was just Grace not being able to count. So this is why I tell you guys that you need to check me sometimes on my counting skills. Okay, so now let's fill in some hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. None here. None here. 9, 10, 11, 12, 13, 14, 15, 16. So I get C, 8, H, 16 here. And then let's see if that holds up on the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, looks good. They seem to have the same formula. And all of these little tick marks are, they're really a lot to look at. So let's erase all of these really quickly. And I'm going to get rid of the formulas too, just because we've confirmed they're the same. They don't actually help us out in the process of determining anything else about the isomers, except that we know now that they are, in fact, some form of isomer and not completely different compounds. Now, do they have the same connectivity? That's a good question. Let's put in some numbers to help us kind of decide. To me, it looks like our longest chain here is kind of right going along horizontally along the page there. And then we have a couple of methyl groups sticking out one side or the other. Again, we're not naming this, but that's just what I'm looking at here as far as a way to describe the connectivity. And then I think we have the same kind of chain shape here with the methyl groups like so. So if we fill in our numbers, 1, 2, 3, 4, 6. Now if we were to describe the position of where that double bond is, in the first molecule, we would say that this is a 3,4 double bond or a 3,4 alkene, right? But in the other one, we would say that that is a 5,6 alkene. So those don't seem to match up. And then we could check and just be really sure to see if our numbering could change this at all if we number the other way. Well, then it would be a 1,2 alkene instead. So it seems like these maybe don't have the same connectivity because in the first one, the alkene's kind of right in the middle of the molecule, but over here it's on the end. So these do not actually have the same connectivity after all, which means that they must be a pair of constitutional isomers. And so for our short fill in the blanks, you'll be labeling those as a C. How did this one go? Did you guess it right? Let's try another one. So here we have a couple more smaller molecules than what we've looked at so far. Let's see if they have the same formula. So we've got an NH2, we've got an OH, and then we've got a CH3 and some other carbons. So let's count up the rest of the carbons. So carbon here, 1, 2, 3, and then this one is 4. So C4, H1, 2, 3, 4, 5. There's none here. 6, 7, 8, 9, 10, 11. So I'm counting 11 there. We'll see how that turns out. And then we have to take account of the other, we call them heteroatoms, anything that's not carbon and hydrogen. So oxygen and nitrogen. C4, H11, O, N. Now let's see if that stacks up over here. 1, 2, 3, 4. 1, 2, 3, 4, 5, none here. 6, 7, 8, 9, 10, 11. There. Seems good. And then again, still the same oxygen and nitrogen. Except I put them in a different order this time. That doesn't matter as far as determining our formulas, as long as the numbers of everything are there and correct. So I'm going to remove all of these annotations, but it seems like these do have exactly the same chemical formula. Now, let's see if they have the same connectivity. It seems a little bit weird, right? Because pointing over here is the nitrogen and pointing over here is the oxygen in that sort of similar position. But that doesn't mean that the connectivity is necessarily different. So let's put some numbers in to say here if we start, well, actually let's start at this carbon because this carbon right here has the most number of interesting things on it. So 1, 2, 3. So we could say that there's sort of a 3-carbon chain on both of these. And then carbon 1 has all the bonds to the interesting stuff, right? Carbon 1 has a bond to nitrogen, a bond to oxygen, and a bond to another carbon. And so that's true over here as well. Bond to oxygen, bond to another carbon, bond to nitrogen. And then 2 is a CH2, and 3 is a CH3 in both cases. So these do also have the same connectivity. Again, connectivity is not taking into account what things are wedged and dashed. It just means that the bonds are in the same places, going to the same atoms. Now we have to look for a ring or a double bond, and I don't see either of those here. So we have to check for R and S to see if we have a pair of enantiomers or not. Let's prioritize our groups here. Between oxygen and nitrogen, which group is higher priority? Get out your periodic tables as needed. Oxygen is the highest of those two priorities. Then nitrogen in a close second. And then we have to decide between a CH3 group and this 2-carbon chain or an ethyl group. So again, whichever has the most bonds to higher atomic number elements, that's going to be more bonds to more carbons, is our ethyl group. And then our CH3 is the lowest priority thing. So lowest priority will often be hydrogen, but not always. Okay, let's get ready to assign our circles. Let's start on this first one here on the left. We've got 1, 2, and 3, and double check that our fourth thing is going away from us in the back of the page. That's good, so we can assign this as is from 1 through 2 to 3. That looks like that is going this silly way around a clock. So that is our S isomer. Let's see if we get R for the other one. Before we assign our circle here, we have to note that our CH3 group, our fourth priority thing, is pointing out at us. So we're going to have to switch our designation. So if we go from 1 through 2 to 3, now that looks more like the right way to go around the clock. That looks like it's R, but we have to switch the designation because of this CH3 group coming out to the front. So this one is actually also S. So if we get S for both of them, what that means is that they have the same identity. They're both the S isomer of this compound. And somehow we've just managed to draw this one in a way that looks different from what we started with. But it doesn't mean it's not the same thing. So in the end, these two end up being the same sign or the same S designation. So these are identical compounds. So for that, I will either have you put the letter I for identical, or maybe I'll have you put the letter S for same. They're the same molecule. Just read the directions to be sure which letter you should use. How did this go? Are they getting easier? Let's do just a couple more, and then you can practice some more on your own. So for this next example, I'm already seeing some things that I'm a little bit suspicious about. Let's just continue through our steps, and even if you think you know what the answer is just by looking at them quickly, it wouldn't hurt to go through these steps in order and just see where you end up. So let's do as we have been doing the whole time, checking for the same formula first. So both of these appear to have a 6-carbon ring in them. They have some kind of a chain coming off the side and an oxygen at the top. So that all looks the same, but let's actually count it up. So number of carbons, 1, 2, 3, 4, 5, 6, 7 here, and 1 oxygen. And here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to double check my count just to make sure that I'm not wrong here. 1, 2, 3, 4, 5, 6, 7. So that's a C7. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay, so I don't think I'm counting wrong. You guys, like I say, always check me on it. But I'm pretty sure that we have an extra carbon over here on this sort of chain coming off of the ring than we do on the previous molecule. So at this point, you don't even have to bother counting the hydrogens. It doesn't matter. They're not the same. They don't have the same number of carbons. So since they don't have the same formula, these are just totally different molecules. And so we're done. That was pretty quick, huh? Our short abbreviation for different will probably be D to fill in to say, you know what, these have very little in common, actually, despite the fact that they look a bit similar. They're not as similar as isomers are to one another. All right, last one. Feel free to stop and make a prediction here if you'd like. Let's see if they have the same formula. 2, 3, 4, 5, 6, 7, 8 carbons there. 1, 2, 3, 4, 5, 6, 7, 8 carbons here. Okay, looks good. C8 for both of these. Let's count up the hydrogens. One of them is already drawn in for us here. 1, 2, 3, 4, 5. None here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And over here, 1, 2, 3, 4, 5. None here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, looks good. There are no other interesting atoms that we need to be looking at, so that's okay. And let's go ahead and get rid of all these annotations so that I can think straight again. There's too many lines and I start to get confused. Okay, so they do have the same formula. Good. Now, let's see if they have the same connectivity. So to me, again, it looks like we have a long chain here kind of horizontally along the page. Let's give those some numbers. 1, 2, 3, 4, 5, 6. And then it looks like in both cases, at carbon number 3, there's a double bond that has a methyl group on one side and a hydrogen on the other. So that seems okay. If we want to give these other carbons some letters, just to make sure that it really does match up as far as the connectivity is concerned, we can call them A and B. You can number and letter these however you want. You can call these anything you'd like to. These are just the way that I like to do it, but do whatever works for you. So we have a 3 to A alkene in both cases, and then A is bonded to methyl group B. So these definitely look like they have the same connectivity to me. Do we have a ring or a double bond? Yes, now we definitely have a double bond that we need to contend with. So if we have a double bond and we think these don't look exactly the same, they're not the same exact molecule, right? Because they're things are pointing in different directions. We can give a cis or a trans configuration to say, oh, okay, I know one of these is this and the other one is the other. So let's remove our annotations here quickly so that we can assign some priorities on these alkenes. So let's go ahead and assign on this one, and then we can fill the priorities in on the other one. First things first, we do our hamburger cut and look at either end of the alkene. On this end down here, we have carbon, right, versus hydrogen. So the carbon gets our higher priority, and the hydrogen we don't really care about. On the other side of the alkene, we have 2 carbons on this side and 3 carbons on the other side. So the 3 carbon side is the higher priority side. And then we can change our line here and do our hot dog cut along that alkene and say, oh, okay, yeah, the star looks like it's on opposite sides of the line here. So this is probably a trans alkene. Let's see if that matches up in our other molecule. So again, we know what the priorities are. I'm just going to put this line in here to remind us where we are looking. We want to decide between this methyl group and this hydrogen. Methyl group is higher priority, and up here, the 3 carbon side of the chain is higher priority. Adjust our line to be the hot dog line, and now we can see that the stars are on the same side of that line. So this one is indeed our cis alkene isomer. So this is a pair of stereoisomers. So I will either ask you to say stereoisomer, write the word stereo, or maybe I would ask you to write C-T for cis and trans pairs of isomers. So with that, There's some examples for you of how I do this kind of flowchart method to systematically decide what the relationship is between two given compounds. If this method works for you, great. I hope you can use it and have some success with it. If it doesn't work for you, figure out what does work for you and then stick with that method. If you need help figuring out something that will work for you, or if you want more help practicing through this type of method, just let me know. Send me an email or stop by office hours. Until then, take care.